everyone. Thank you for joining us today and welcome to our presentation of Seymour, an open source, easy to configure, active monitoring solution. My name is Katarina and I'm here today with my colleagues, Scott, Tim, and Miles. And we are very excited to introduce you to the project that we worked on for the past several months as a fully remote team spread over the US and Europe. But what is Seymour, you may wonder? Seymour is an active monitoring solution that allows users to simulate requests from globally distributed locations to test their API endpoints. Seymour measures performance, uptime, and correctness of the payload data. We built Seymour to help engineering teams bolster existing testing approaches and handle the challenges of monitoring their increasingly complex systems. Our solutions enable rapid detection of issues in production before users experience them. And moreover, Seymour's infrastructure is easily deployed with a few CLI commands and a quick setup. But before we continue, let me just give you an outline of our presentation structure. We'd like to begin with an overview of what problems we designed Seymour to solve, after which we'll explain what active monitoring is and why it is essential in assuring the health of a system. Next, we go into explore existing solutions in the active monitoring space, their advantages and limitations, and where exactly Seymour fits in the picture. We'll then present a quick demo of Seymour and how it is deployed, followed by a discussion about its underlying architecture. Afterwards, we'll talk about some of the design decisions we made and challenges we encountered along the way. Next, we're going to cover some additional features we'd like to work on in the future. And finally, we'll finish with a Q&A. But before we dive further into Seymour and active monitoring, let's take a step back and talk in general about how development teams minimize the risk of bugs reaching production. Many of the techniques for accomplishing this fall under the category of testing. Software testing is the process of evaluating and verifying that a software product or application does what it's supposed to do. Good testing helps to prevent bugs and can sometimes even help to improve performance. How is software normally tested? Well, typically, tests are either run locally during development or in staging environment, just prior to deployment. Software tests are generally categorized based on purpose and scope, and there are many different types of tests. Two common examples that we will talk about are unit tests and integration tests. Unit tests are a type of test which focuses on a small part of an application. The unit might be one or many classes or functions. These tests are often run by an individual developer frequently after making even small changes to a code base. Unit tests can also be run as a part of CI/CD pipeline. Another example are integration tests. In this approach, different parts of an application are tested together as a whole. These tests can find bugs in the interaction between components in a way that unit tests are not designed to. Remote systems, however, are often mocked. In spite of developers' best efforts, issues still do arise in production. How can this happen, you may wonder? Well, first of all, conditions change. Integration tests are often performed only on deployment, meaning these tests are run only at a moment in time. Secondly, replicating production isn't always possible. Sometimes only nearly perfect replication occurs in pre-production tests. And this is especially true of modern distributed systems. And finally, third-party service dependencies can prove to be unreliable. On Martin Fowler's website, a contributor wrote this pertinent quote. In the age of small independent services and frequent deployments, it is very difficult to test pre-production with the exact same combination of versions as they will later exist in production. So what happens when issues do arise in production? Well, the end user's experience may be degraded or even completely broken. For example, Response time can be higher than expected. The response data can be incorrect, and maybe worst of all, an API can be unavailable altogether. Rather than waiting for users to experience and surface such issues, it would be convenient to test API endpoints in production continuously. And this is exactly where active monitoring comes into play. But what is active monitoring specifically? Active monitoring, also known as synthetic monitoring, is a technique that runs automated tests against a live production system in order to detect failing business requirements. It helps to continuously monitor server and application performance, even during periods of low user engagement. Active monitoring is generally used to test three things: availability or uptime, performance, which is a measure of latency, and correctness of data. Tests are written with API consumer expectations in mind to ensure the API provider continues to meet its commitments. Let's zoom in a bit and have a look at how a single test might look like. This test, called My API, comprises of two assertions. Here, a GET request sent to our example endpoint should return a response within 500 milliseconds. The actual response was completed in 632 milliseconds, so the assertion would be considered a failure. The other assertion expects the response status of 200. In this case, the expected value was 200, meaning the assertion is considered passing. But because our first assertion failed, the overall test is still considered failing. In the event a given test fails, on-call engineers can be notified through various channels, such as Slack or email, and begin troubleshooting the underlying problem. Now that you know what active monitoring is, let me talk briefly about why is it even important. But simply stated, things are bound to go wrong in any software production environment. But rather than view this as a bad thing, however, engineering teams can see it as an opportunity. They can use active monitoring to identify problems in production before users do. Active monitoring is especially important in the context of microservice architecture. Take, for example, an API endpoint that is dependent on many different services, both internal and external, each of which may be deployed multiple times per day. Including a replication of all these services in local or CI tests would be slow or brittle at best. Including some services may not be feasible at all. So even with a well-maintained test environment, functional and data errors can still slip through the cracks and make their way into production. For the users of a company exposing public APIs, the source of truth is what the experience is when they hit one of these endpoints. Furthermore, active monitoring solutions often provide the ability to originate tests from locations around the world. This provides insight into how a system is performing for users in specific geographic locations and helps to better diagnose if an issue is network-related. By introducing active monitoring in a holistic testing strategy, engineering teams can sleep better at night, knowing that bugs in production will surface fast and be fixed before users are impacted. I'm now going to pass it to Scott, who will start by discussing existing active monitoring solutions.
Thanks, Katarina. Now that we better understand what active monitoring is and what problem it solves, let's get an overview of the existing solutions and see where Seymour fits in. There are quite a few products offering active monitoring solutions. Some prominent vendors that offer this service are New Relic and Datadog, followed by some smaller scale companies like Uptrends, Checkly, and RunScope. There are also a handful of open source solutions such as Artillery, which is more commonly known for load testing, and Monica. Besides using a SaaS or open source active monitoring product, some teams may decide on a DIY approach and build their own in-house solution. Let's weigh these options by considering their various capabilities and feature sets. In other words, What are the pros and cons? Let's take a look. In general, SaaS active monitoring products offer geographic distribution of request locations. Typically, these solutions are managed, meaning there's very little to zero setup required from the customer to configure their first test. Additionally, most of the interactions with these SaaS products, including New Relic and Checkly, are through a UI, which makes setting up new tests easy for all users, including non-engineers. One drawback of a managed solution, however, is the lack of data ownership. This might be a deal breaker for some companies who don't want their data residing on a third-party provider's infrastructure. SaaS solutions typically offer a wide variety of features, including native alerting over a variety of channels. Some additional features include teardown scripts and integration into CI/CD pipelines. All of this functionality, some of which might not be needed for a given use case, does come at a direct financial cost. SaaS solutions are the most expensive option. On the other hand, choosing an open source active monitoring product allows users to maintain complete control over their data. One drawback of these solutions is that they do not typically offer geographic distribution of tests, at least in their free tiers. Additionally, these solutions are more laborious to set up and use as compared to their SaaS counterparts. Both Monica and Artillery, for instance, are set up via a multi-step process, and tests are configured via YAML. There is no UI. On the other side of the spectrum, we have in-house solutions. This could either entail building a system from the ground up or wrapping an existing open source product like Monica. A major appeal of this approach is that by definition, the user can customize the product they build to fit their specific needs, which can of course include maintaining complete control over their data by hosting it on their own infrastructure. A significant drawback of this approach, however, is the amount of time and effort needed to develop such a solution. It would require engineering resources that could be otherwise spent on more mission-critical tasks. This brings us to Seymour. Having surveyed available active monitoring solutions, what we found was lacking was an open source, self-hosted, easy to configure option that allows running tests from globally distributed locations. And that is why we built Seymour. Seymour has geographic distribution. Users can configure tests originating in 22 global locations. Seymour is easy to use. Although not as simple to set up as a managed SaaS product, as we'll discuss later in the presentation, provisioning Seymour requires only 2 CLI commands. Once it is set up, all test and alert configuration are done through a UI, although Seymour also exposes an API enabling programmatic configuration if that's what the user prefers. Because Seymour is open source and self-hosted, it allows users to maintain sole ownership of their data. Seymour enables users to configure alerts to be sent over 1 or more of 3 channels: email, Slack, and Discord. And finally, since the only cost of Seymour is the cost of the AWS infrastructure it runs on, it's inexpensive, especially relative to its SaaS peers. Now that you know a bit about active monitoring and Seymour, let's take a tour through the Seymour UI and explore how to create a test and view the results. The first thing I see when I visit the Seymour homepage is a table view of the existing tests. This table includes some basic information about these tests, including the name of the test, a summary of the 3 most recent test results, and how often the test is scheduled to run. This table also includes buttons enabling the user to delete, edit, or trigger a run of the test. I can begin the process of configuring a new test by clicking the Create Test button, which takes me to a form with several inputs. First, I need to name the test. I'm going to call this Seymour Demo. Next, we'll configure a request to hit the specific API endpoint that we want to test. I want to test an endpoint that some members of our team worked on that's part of a task management API modeled after Trello. Let's test the endpoint used to create a new card. This is a post request to this URL. This endpoint expects a request body of a particular shape, so let's add that now. We don't need to add any custom headers for this request, so we can skip this section. Now that I've configured the request, I can add some assertions about the response received from the server hosting the API. Let's begin with the response time. I want to make sure that the response time is less than 500 milliseconds. Next, I expect a status code of a successful request to this endpoint to be a 201, so let's add an assertion for that. I also want to make some assertions about the response body. First, that the response body contains a title property equal to what we indicated in the request body. The $sign here represents the body of the response, so $.title is how we indicate that we want the title property of the response body. Next, the response body should contain a property completed that's equal to false. And include a null due date property. The server should generate an ID for the card and attach that to the response body. Let's add an assertion for that. Finally, let's add an assertion for the connection header. It should have a value of close. That's it for assertions. Now, I can choose the locations from which I want the request to originate. Although the API we're testing doesn't yet have users all over the world, let's pretend that it does, and that we want to make sure that any clients of this API in a variety of geographies will not experience unacceptable latency when interacting with this endpoint. Let's select North Virginia, Stockholm, and Montreal. Finally, we'll configure the frequency of the test and how we want to be alerted in the case of an assertion failure. Let's configure the test to run once every minute. If any of these assertions fail, I want to be alerted on Discord. I now need to paste in a webhook address for the Discord channel on which I want to be alerted. Although I chose to be alerted on a particular Discord channel, I can add as many alerts as I want and can choose from other alert channels such as email or Slack. With that, we've completed the test configuration, so let's save. We can now see that Seymour demo has been added to the top of the table of tests. I could trigger a run of that test by clicking the Run Now button, or wait a minute in order for the results to start to populate. Either way, we need to give it time to run. So for now, let's click into another test that already has results, and we can come back to the test we just configured at the end of the demo. So here you have a summary of the test, meaning an aggregation of the results from each time the test has been run. We can see that 100% of requests have succeeded, which means no 400s or 500s. But don't be mistaken, a successful request does not mean that the test assertions passed. It only means that the response to the request was successful as indicated by its status code. Next, we can see that we have had many assertion failures. We will dig into what might have been the cause for one of these soon. And then we have a basic summary of response times, including the median and the 95th percentile values. We also have some basic information about the 3 most recent test runs, including the region where the request was made from, the status code, the response time, the number of assertions passed, and when the run of the test was completed. Below, we have a graph of the response times broken down by each of the different regions that the requests are originating from. So we can see here that the response times from Stockholm, for instance, are higher than those originating in Montreal and North Virginia. This makes sense since the endpoint that we're hitting is served from North America. To see more than just the 3 most recent runs, we click See All Test Runs. Let's click into the most recent run of this test as it has a failed assertion. This test was completed on August 10th, and the request originated from Stockholm. Although we received a response, this test is labeled a failure due to the actual response time of 747 milliseconds exceeding the target value of 500 milliseconds. All of the remaining assertions have passed, and we see a summary of the target values and the actual values. We can also review a collapsible response body and the response headers. Okay, let's head back to the tests view. We can now see that there are results for the test that we configured, including several failures. Let's click in. The failure of this run of the test was caused by a response time again. The actual response time was 921 milliseconds, whereas the target was 500 milliseconds, just like we configured. And that means we should have been alerted on Discord. So let's go check that out. Sure enough, we can see here that we have alerts for this test with the details of the failure. Now that you've seen the UI demo, let's talk about how to get started with Seymour. An AWS account is required, but once that's set up, all that's left is to 1, clone the Seymour infra setup repo, 2, run 2 CLI commands to spin up the necessary resources in your AWS account, 3, enter the generated URL in your browser. And with that done, you are ready to configure your first test. One thing worth noting, however, is that the provisioning of AWS resources, while automated, may take upwards of 20 minutes, primarily due to the provisioning of resources in 22 remote regions. I'm now going to hand it off to Miles, who will take you through the details of Seymour's architecture.
Hey, thanks for walking us through that, Scott. All right, now that we've seen what it's like to interact with Seymour's UI, let's take a look under the hood at the infrastructure and see what it's doing to make everything work. The infrastructure can be thought of as loosely organized into 4 main sections, which together make up the lifecycle loop of a single test. First, we have test configuration, which you got to see a demo of before, but we'll look into what is going on behind the scenes. And then there's a pre-processing phase, which preps each test run with the test configuration and proper routing to the geographic regions where it's needed to run. Now we get to the main event, test execution, where the actual HTTP request is made to the endpoint and the response is checked against the assertions in the test configuration. The results are packaged up and sent to the final phase, post-processing, where we handle storing test results and alerting for failed tests. Before we're going on, let me address home and remote regions real quick. When you deploy Seymour, you select your main AWS region in which to set up the infrastructure. And that's what we are referring to here as the home region. And it, in fact, holds most of the infrastructure. Everything needed to power the UI, the backend server, as well as everything for the test configuration, pre-processing, and post-processing phases. The test execution needs to happen in any number of the AWS regions selected when configuring a test, so the infrastructure for that phase is set up in all other available AWS regions, which we refer to here as remote regions. Next, let's take a turn in each phase to walk through the details of a single test journey through the loop. The journey of a test through the infrastructure begins as a JSON configuration file sent from the UI when a user first schedules a test. The backend app stores the test config in the database, assigns it an ID, and then passes it to EventBridge, a serverless event bus often used in AWS-based event-driven architectures. We are using EventBridge as our scheduler service. Each test is stored in our scheduler as an EventBridge rule, a scheduled action that fires at a fixed recurring interval. The test configuration is saved to the rule as a payload that will be sent to its target every time it fires. That's it here. And in fact, as we'll see in the next several slides, the backend app isn't needed at all during the ongoing life of a test once it has been scheduled. This, the pre-processing phase, is where each scheduled test run fires off and where our JSON test config kicks off through the loop. We previously walked through what scheduler is doing, so we know that the rule fires on a schedule, but I left off the target for where the rule fires to. The target destination is a Lambda function we refer to as route packager, and it's the same target for every rule that is scheduled. Lambda is an AWS serverless compute service that lets you run code without having to provision or manage servers. Route packager's purpose is to read all the location data from the JSON test configuration payload and prep it for routing to the correct regions. It then publishes a message with the test to a topic in SNS, Amazon's simple notification service. A queue in each region is subscribed to the topic and will only accept messages if they are intended for that region. Up to this point, all the infrastructure we've looked at has been within the home region. This, the test execution phase, is a look at what is going on in each remote region. As I mentioned previously, there's a queue that first receives the message in each remote region. The message is pulled from the queue by a Lambda function we refer to as test runner. Now, the JSON test config has made its journey to the point where it's actually needed for making the HTTP request. Test runner uses the config data to make a request to the endpoint and then compare the response to the expected response values in the assertions. If any of the assertions fail, then the whole test is marked as failed. It then packages up the results and sends them back to the home region. Back in the home region again, the test results are received in a queue. They are processed from the queue by a Lambda function we refer to as test result handler. Regardless of whether the test passed or failed, result handler writes the results to the database. However, when it first examines the results for whether the test passed or not, if it finds that the test failed, it immediately invokes another Lambda, which handles alerting. When the alerting Lambda is invoked, it receives in its payload information about the test which failed. It then queries the database to get that test's alerting information and sends an alert message to each configured destination. Here, you can see an overview of the entire system. From the test configuration coming from the UI and making it to the database and into an event bridge rule, then how that rule fires off for each test run and is routed to the correct region for the actual test, all the way back to storing the results in the database and alerting for failed tests. I'll now pass things off to Tim, who's going to discuss some of the decisions and challenges we encountered while building Seymour.
Thanks, Miles. Let's dive right in. During our project research phase, after the team settled on our problem domain, we were quickly faced with a critical decision. Should we wrap an open source project to achieve our goals, or should we build something from the bottom up? Let's take a closer look at Monica, one of the open source projects Scott discussed in his overview of existing solutions. This project was especially compelling for us because it offered a lot of the functionality that we wanted to provide to Seymour users. Monica is an active monitoring tool designed to send out user-defined HTTP requests on a schedule and assess the responses. Out of the box, Monica can run complex API tests on scheduled intervals, handle alerting through integrations with a number of popular platforms, and being open source, users are able to maintain ownership of their data. We used Monica quite a bit in our research, and while it works well, it was still lacking critical features that were important for our use case. First and foremost, Monica lacked the ability to originate tests from a variety of geographic locations. It's limited to sending HTTP requests from the server instance the app is running on.
We also homed in on the difficulty of using Monica, which is a command line tool and does not come with a UI. As Scott mentioned earlier, one of our goals was to make tests easy to configure. With a solid understanding of Monica's capabilities and limitations, we then took a hard look at wrapping and extending Monica to achieve all of our requirements. If Monica could provide many of the components for Seymour, we could focus more time on additional features, or so we thought. After assessment, we felt that we could add a UI and expanded metrics with relative ease. A much bigger challenge came into focus when we looked at multi-region testing. Because Monica requires a constantly running process, in order to give our users the option to generate multi-region tests, we would have had to deploy the app to dedicated virtual machines in each of the 22 AWS regions we plan to support. This approach presented a number of thorny questions. First, each virtual machine would require security, networking, and application configuration upon deployment. How would we make that easy for the user? Next, to generate tests, a Monica instance must read from a local YAML configuration file. How would we make sure that the config files were all in sync across the virtual machines? Lastly, 22 virtual machines would be inherently difficult to maintain. How would we ensure the reliability of what was supposed to be an easy-to-use monitoring tool? And furthermore, even if we were able to answer these questions and Monica was distributed across regions, how would we then send the test results back to the home region where the data would be processed? After researching potential solutions to these problems, we determined our entire project architecture would have to be oriented around Monica. Ultimately, we determined that bending the infrastructure to accommodate only a portion of the functionality was suboptimal, and that by developing our own solution, we could avoid these challenges. As Miles demonstrated in his overview of Seymour's architecture, we ended up utilizing Lambda functions to achieve our requirement of multi-region testing. Instead of deploying an entire virtual machine running Monica to remote regions, Seymour simply deploys the test runner Lambda function coupled with a queue. Although we had to write more custom code, we found this setup to be superior in the following ways. First, the test runner Lambda function is easily deployed to all regions with AWS's Cloud Development Kit, or CDK. This eliminates the need to configure any virtual machines. The test runner Lambda function is stateless. All of the scheduling and configuration logic remains in the home region and is communicated to test runner via SNS, AWS's message broadcasting tool. And by placing a queue in front of the test runner Lambda, we get a high degree of assurance that test runner will process incoming SNS messages. Communication of test runner's results back to the home region is simple, thanks to Lambda's ability to send invocation records to a queue destination in another region. And rather than a constantly running virtual machine, the test runner is invoked on demand. This reduces maintenance needs and also reduces costs. Finally, Lambda functions scale on demand out of the box. If a user configures dozens of tests to run in the same region at the exact same time, test runner can handle the load. In the end, by building Seymour from the ground up, we were able to fully take advantage of AWS cloud native products, resulting in an easy deployment and low maintenance user experience. Our journey to building the route packager Lambda function also comprised an interesting set of design decisions. If you recall from the walkthrough of Seymour's architecture, route packager is the target for all scheduler rules. Also recall that rules, in the context of Seymour, are simply scheduled events with an attached JSON test configuration. We knew from the outset that we wanted to enable geographically distributed testing locations with an efficient use of resources. Deploying test runner to all remote regions achieved part of this plan, but how to communicate scheduled test configurations to test runner was not immediately apparent. One option we looked at was directly invoking remote region test runner lambdas from the scheduler rules. While EventBridge is technically capable of this, there is a five target limit for any given rule. Because we wanted to support 22 targets, one for each region, we quickly discarded this approach. We also tried using EventBridge's event bus functionality, which is essentially another interface for communicating events in AWS to connect home and remote regions. This approach denied us the ability to easily pass through test configuration JSON data, however, and was also discarded. Ultimately, we landed on using SNS as the medium through which scheduler events were distributed because of its ability to widely broadcast a message containing the test configuration across regions. While this setup was effective, it lacked efficiency because for every rule that fired, a corresponding message would be delivered to every test runner Lambda. This was not ideal because every message would invoke all test runner Lambdas, causing each to spin up and execute some code to check if it was an intended target, resulting in wasted compute time. In order to make this message distribution more targeted, we added message filtering logic to the SNS topic subscriptions for each region so that only messages intended for a given region were added to the queue for processing by test runner. We still needed one last piece of functionality to make this work, however. In order for the subscription filters to work, we needed to add some region metadata to the message, functionality that EventBridge does not provide. This is why we decided to build the route packager Lambda function. In Seymour's final architecture, each fired rule first travels to route packager, which translates the location data from the test configuration into attributes that it adds to the message before publishing to the SNS topic. The location attributes are then used by the subscription filters to ensure that the test configuration is only sent to the relevant remote regions. So by combining route packager and SNS in the pre-processing phase of Seymour's test loop, we were able to achieve our goal of efficient distribution of tests to the remote regions. At this point, I'd like to highlight how our collective design decisions resulted in a high level of overall system resiliency. Resiliency was at the top of mind at each phase of building Seymour because after all, what good would an active monitoring tool be if it was brittle or prone to crashing? There are three pillars in Seymour's overall approach to system resiliency. First, we reached for AWS's serverless offerings, including Lambda functions, throughout the test loop. As discussed in the wrap versus build section, using serverless allows Seymour to shift a good portion of operational responsibility and infrastructure management to AWS. Furthermore, by using AWS's managed messaging services, we were able to decouple individual components within the test loop, as well as the test loop from the rest of the system. This design provides assurances that test runs will be processed eventually, even in cases of extremely high volume, or if one of the loop components fails. As Miles mentioned earlier, once a test is configured, it is able to run and generate alerts, even if the UI and backend app go down. Lastly, we chose to deploy the backend app using AWS's Elastic Beanstalk service, which reduces the risk of failures through automatic capacity provisioning, load balancing, and auto scaling. Because the underlying infrastructure is fully managed by AWS, Elastic Beanstalk also provides automatic failover for terminated or unavailable instances. In addition to some interesting decisions that our team had to make while building Seymour, we also encountered some challenges along the way. One of the foremost challenges we faced in building Seymour was automating the deployment of AWS resources across multiple regions. Because ease of deployment was one of our main goals for the project, we wanted to limit as much as possible the amount of infrastructure configuration required of the user. The main tool we used to deploy resources was the Cloud Development Kit, or CDK, which is an AWS service used to programmatically set up, modify, and tear down resources. The CDK was relatively straightforward to work with for deploying and connecting infrastructure within the home region. However, this same approach did not work when it came to connecting resources between the home and remote regions. One way of implementing a multi-region deployment is using a CDK pipeline. However, we continued to look for a different way because of the additional burden of complexity caused by adding the pipeline. There would be the one-time technical burden on us to implement the pipeline, but it also added several more pieces of complexity for the eventual user just to get Seymour deployed on their own account. Technically, this would work and it remained a fallback option for us. Ultimately, we were able to avoid having to use the pipeline. We did this by using a different AWS tool, the Software Development Kit, or SDK. While the CDK is specifically purposed for setting up, modifying, or tearing down resources, the SDK enables cross-region communication at runtime. We added some code to the test runner Lambda function so that when invoked, it can use the SDK to connect to the home region. This kept the deployment process lean and the complexity to a minimum for the installing user. While we are pleased with the capabilities that Seymour offers, there are still a few things that we would like to add to the system. As it's currently configured, Seymour will trigger an alert for every failed test. In practice, this means that if a user has a test running from 10 different locations and the same assertion is failing for each distributed test, the user will receive 10 different alerts for each configured alert channel. If this test is configured to run on a tight interval, say every 1 minute, well, you get the idea. You're going to have a whole lot of things chirping at you. Going forward, we'd like to implement a feature allowing users to select alert thresholds as well as alert aggregation options. Teardown scripts are custom scripts supplied by the user that are intended to execute after a test is run. A teardown script could be used, for example, to send an additional request to clear out any test data generated from a post-request test. As it stands, the user will have to rely on other mechanisms to clear out data generated by Seymour in their production system. Lastly, Seymour tests are designed to run on a set schedule, but can also be triggered on demand with the Run Now button. In the future, we'd like to give users the ability to trigger tests from a CI/CD pipeline, so Seymour can be fully integrated with DevOps processes. And that's all we have for you today. Thanks for listening, and now we'll take any questions.
All right, let's just wait a minute, see if we get some questions come through the Q&A. All right, that was quick. All right, question we have come in here. What was the most challenging and the most exciting part of working on Seymour? Yeah, I can start off here, I guess. I imagine we each probably have our own opinions here. The most exciting part that first comes to mind was the working on something with the overall geographic distribution of tests. It just seemed kind of cool to be able to build something that could test and make sure that this thing is working from all these different locations around the world. And that kind of fits into some of the most challenging, as we talked through in working with the CDK part, getting the home region and remote regions connected together. It had some challenges in there working with the CDK, but it was very rewarding.
I can go. I think, yeah, from a technical perspective, learning the various AWS resources that we could use to implement our design was really interesting, in an area where I learned a lot. What was most exciting for me about the project, and this is at sort of a high level, is that it actually feels like Seymour does fill this niche that's not addressed by the existing solutions. As far as we can tell, it is unique in the marketplace. So that was pretty cool. There's still work that would need to be done to get it to a level where, you know, it could be used by a company, but we feel like it actually does address an unmet need.
I can jump in. So for me, I think the most exciting part where we as a team that were deciding about how Seymour architecture would look like, where we had to weigh all the pros and cons of every engineering decisions we made. And I feel like it was very exciting to see how the whole infrastructure grew with time as we were adding those new components and functionalities. And I think at the same time, it was also the most challenging part, as we knew that every decision we make will have its own consequences, which kind of the weight might be hard to predict beforehand. So each of the decisions we had to take needed to be carefully thought through. So that was quite challenging, I think.
Yeah, just to piggyback a little bit on what's already been said, you know, during our research phase, the global distribution of tests really sparked my imagination for this project and, you know, got me excited and motivated. Not to say that I wasn't already, but also speaking for myself, I had never used AWS before. And so, you know, the team as a whole had to ramp up quickly in terms of, you know, learning how AWS works and also, you know, how to connect the different pieces. And felt like towards the end, we were speaking an entirely different language than where we started.
Yeah. Okay, I have another question here. How did you come up with your project idea? Someone want to jump in on that?
Sure, I can jump in. Yeah, we originally were interested in the concept that things do go wrong in production, which led us to look into testing. That led us to this concept called fuzz testing, which is designed to is different than what Seymour is, but it's an interesting topic for generating edge cases in your tests that developers might not think of, and that led us to active monitoring. And then once we discovered this area and started to learn about the products that were offered by the SaaS solutions and the open source projects, we thought we might be able to build something interesting.
Yeah, and that kind of hits, I see another question here. Where did the inspiration to build Seymour come from? I feel like you kind of hit that there, Scott. I also have another question here. Did you choose EventBridge only for scheduling functionality? Have you considered other options? I could take this, actually. We started off originally just thinking about the scheduling functionality. You know, what's something we can do to have this test fire off every 1 minute or 5 minutes, whatever it is. And when we're looking at the different services or products that AWS has, EventBridge jumped out for that. But as we got into it, it's really it can do a whole bunch of different things. And Tim kind of briefly talked about it in his discussion of how we were developing Route Packager, in that it is used for event-driven architectures and it can send like event messages. And so we played around with using that part of EventBridge as well. We considered building something for ourselves for the scheduling part of it, but in the end, the solution kind of just coalesced as we looked at combining a few different things into the final architecture that we ended up with. Okay, I have another question here. You mentioned data ownership as a con for your larger enterprise solutions, such as New Relic and Checkly. Can you speak about what you mean here a bit more? What data would normally be sent in these larger enterprise solutions?
I can take a stab at that one. So when we talk about data ownership, what we had in mind particularly was some sensitive data like healthcare data or financial data. So when it comes to testing and production, you know, that means exactly like it sounds. Live data is going to be flying around, for lack of a better phrase. When we looked at the SaaS solutions, including, you know, Datadog, New Relic, Checkly, what happens is that the data generated from, you know, an API endpoint actually makes its way to the SaaS provider servers where the sessions checks are run. And that data is also saved so that you can view results in a future date. So we surmise that that could potentially lead to some, privacy issues in certain contexts. And so we like this idea of allowing the users to maintain control of the data and self-host, so that that would, potentially solve an issue for them.
Yeah, and I have another question here. What's the most valuable thing you learned as a software engineer while making Seymour that you will take on to future jobs?
I would say working in a team. It took a little bit of time to ramp up and get our processes all in sync in terms of Git workflow and collaboration in terms of the architecture and weighing design decisions and trade-offs and things like that. But towards the end, we were firing on all cylinders, and everyone was bringing something different to the table. And yeah, it was a very good experience.
Yeah, I have to second Tim's comment there. The teamwork, it was at times challenging, but just seeing the way that everybody's different strengths and weaknesses, started and then morphed, and we each kind of fell into different roles and worked together. That was really satisfying. I enjoyed that process too.
Yeah, I agree with both Tim and Miles. Definitely working as a team was very important. And there were obviously many challenges with that, but I feel like our team did a really good job with communicating. Apart from that, I think that also that researching technical topics was, for me, something that was very interesting and a very valuable thing to learn. How to research a project, how to find idea for a project, and how to finally create something together as a team, something that other people can use and have use in a daily life. So yeah, I think that was very valuable.
Yeah, I agree with the rest of the team here, that the teamwork aspect of the project is something that I learned a lot from, and that I'll take with me into whatever is next. And then on a very tactical level related to the teamwork, implementing having processes in place with our repos where we would have automatic deployments just solved a lot of headaches we had early on with, some Lambdas being out of date and only some members of the team knowing that. And so once we smoothed out those processes, things became a lot easier.
Yeah, agreed. All right, I have another question here. To connect to remote AWS regions, does Seymour pass along an ARN during the processing phase? If that is the case, how the heck do you keep track of all the multi-regional infrastructure? Yeah, so connecting to remote AWS regions, it has to do with the queue in each of the remote regions subscribing to an SNS topic. And so it's kind of like this pub sub model where the SNS messenger in the home region is publishing a message to any subscribers that are there. And so each of those queues during the deployment phase, we have set up to subscribe to it uses the ARN of the topic, which is created in SNS. And yeah, the only improvement we made to that was the filtering, which Tim walked us through. That prevents the needless distribution, so that all the queues aren't receiving the message. It's only the ones that have the specific property for its location. Okay, I have another question. What was the hardest bug or challenge you had while building Seymour? Someone want to take this?
I can take, yeah, I can try to answer this question, although other members of the team definitely jump in. It was a we were all working on independent parts of what Miles referred to as the test loop when we began development on Seymour. And then we had a day or two where we all needed to jump into the same chat because we were trying to connect all those parts and see a test go from configuration all the way to being written to having its results written to the database, and just connecting all of those pieces, making sure that the test configuration JSON was uniform throughout the entire loop, which it originally wasn't. There were small differences in naming. Some of us had used underscores or dashes, and so like making all of that consistent was required for the test to make it all the way through the loop. But eventually we sorted that out and learned from the experience that setting up the contract beforehand to have consistent naming would solve a lot of headaches. But once we got through that, things were a little bit smoother.
All right. Can Seymour monitor applications that are not hosted on AWS?
I can take a stab on that one. So the short answer is yes, because we designed Seymour to be, well, we designed Seymour to be cloud specific, because we wanted to take the full advantage of all AWS services that had to offer. But with that being said, Seymour's infrastructure is completely separated from what user might have on their own AWS accounts or any other cloud provider's account. So it is not required at all for the user's infrastructure to be hosted specifically on AWS. However, the user needs to have their own AWS account in order to host Seymour, but not to yeah.
Yeah. Okay, I see a question here down towards the end. What are some tips for researching topics and finding ideas? I mean, first thing that comes to my mind is following something interesting. You know, as Scott, I think you were hitting an earlier question talking about some of our research phase. There was a lot of these API adjacent type things. I remember personally, I was really interested in gRPC and kind of like went down this trail and the fuzz testing. And just as we kicked around different ideas and challenges, I don't know, just seeing the team conversation back and forth, just with some input. I don't know, it kind of, there's one phrase you said, Tim, it fired up your imagination, like the geographic distribution I think you were talking about. And yeah, it's a good phrase I just wanted to take, because getting that imagination, kind of that interest and following it all the way through, I don't know, I think that's kind of what brought us together on this.
And I would even caveat that a little bit, like follow what's exciting, but at first, you know, cast a wide net, because it's easy to kind of dig in and go deep on, like, you know, the first handful of things that you research. But it's often the case that, you know, it's a dead end, or, you know, it doesn't work for X or Y or Z reason. And actually, you know, going back to the build versus wrap discussion, I was on the like wrap side of things at first, and I was like, you know, lobbying hard for that approach. But you know, it's just important to keep an open mind, and my teammates, you know, were able to persuade me that you know, was not ideal for, you know, the reasons I discussed earlier. So I felt like that was you know, one of the biggest takeaways for me during this research is, you know, just have an open mind, and even if you hit a dead end, it informs, you know, the path that you ultimately take.
Yeah, and I see. Oh, sorry. Go ahead. Jump in, Katarina.
I just wanted to add to this one that what we have actually did with our team was we decided to research as many topics as possible So we met every day and maybe researched for 2 hours, tried to find a topic, and then we presented to each other. And if that was interesting, then maybe we were keeping researching day after. But if other team members didn't find it interesting at all, then we would just leave the topic and try to find something else. But the first week of our research was the phase when we were actually didn't dig too deep into specific topics, but we tried to go very broad to kind of have a bigger picture of what's out there.
Yeah, and I see this last question here. It's a good question. How did you determine which team members worked on which of the independent parts of Seymour, and what strengths did each team member bring? Someone want to start on this?
I can start. I think we were really lucky in that all of us were there was overlap in some of the things that we were interested in, but there also was a lot of mutually exclusive things that we were interested in, and so each of us kind of was able to work on the thing that most excited us, and still be able to complete the project. There was, I don't think, really a moment or a particular item that nobody wanted to work on that, you know, one of us needed to put up our hands and say like, okay, I'll do it. It just kind of worked out that each of us had a slightly different set of interests in the implementation.
All right. Nobody else has anything to add there. We can just give it another minute, see if any final questions roll in. Okay. Did you guys have any technical disagreements or conflicts in your group? And how did you handle those? We did, Tim kind of mentioned one of the first big conversations. We'd kind of gotten to a point where we had all agreed on, all right, let's dig in to this idea that, you know, became Seymour. And at the beginning, you might think that you're all in agreement, but as you start having conversations and dig into, well, what would this look like? How would we design this part? You know, what about this piece of the architecture? You realize that maybe your thoughts aren't quite in agreement as you thought. And we probably not halted, but we definitely took a couple days where we really looked at all the different technical aspects of either wrapping Monica or building something from the ground up, because it really felt like it would be this maybe longer trajectory. Like if we wrap Monica, well, then that might lead to this. Well, then how would we solve that? And kind of walking down the whole road of what that would mean. Okay, and if we don't, then will it take more time to build something? What does that mean? Will we have to sacrifice some features? And that was, I won't say heated. I feel like the conversation was actually really, really productive, but just through a lot of conversation, we'd have conversations, do research, come back, you know, just turn the problem around a little bit and look at it from a different angle as a team. That's probably how we handled that. Anybody else want to add anything on that?
I'll add one thing. I think we were really good at not becoming personally attached to any ideas. Like the person who suggested something in general was not emotionally attached to that. And we were able to rely, when it came to disagreements, on listing pros and cons of the options we were considering. And as a team, once those pros and cons had been presented, deciding on the best option. And normally, like after we had gone through that process, it was obvious which thing we should choose, whether that was a database or an infrastructure decision, or even something that was not technical in terms of like how we organize our efforts.
All right, I think we're winding down here. If anybody has any last questions, you go ahead and ask them. We'll give it about a minute and then that's it. All right. Well, I think that is it. Thank you, everyone. We appreciate you coming to the presentation today, and thank you for letting us share Seymour.